In this video, we're going to look at how to solve some problems regarding to the basic buffer solution by using the Henderson-Hasselbalch equation. The formula or equation for Henderson-Hasselbalch for buffer solution looks like this, where you have POH equals to PKB plus log times the concentration of conjugate acids over the concentration of weak base. Do you remember that the concentration of conjugate acids will be the same as the concentration of the weak basis salts? So if you have the information about the concentration of weak basis salts, you can use that one to identify the concentration of the conjugate acid. And from there, you should be able to plug in that value into the Henderson-Hasselbalch equation. Let's have a look at a question. Right here, the question wants you to find out what is the pH of the buffer solution. And when you read the question from the top, the buffer solution that we have over here is a basic buffer solution. It's involving ammonia NH3, which is a base, a weak base with the salts. So that is the salts right there. And then another clue that we have been given to tell you that the buffer solution that we need to work with in this question is basic is from the Kb value given to you. So if you are given the value of Kb, even though the question doesn't say that it's a basic buffer solution, but since you have the Kb value is given, this is the clue that is telling you that the whole thing over here will try to work out with a basic buffer solution. It's very important for you to know whether it's going to be acidic buffer solution or basic buffer solution. Why? Because when you want to find the pH for a basic buffer solution, it's slightly different from what you have done for acidic buffer solution. So to find the pH of a basic buffer solution, step 1, we have to find out what is the value of POH first by using the Henderson-Hasselbalch equation, of which that we have seen just now in the beginning of the video. And then from there, after you have found out the value of POH, we're going to use the formula pH plus POH equals to 14 to get the value of pH. So as you can see over here, it is not as straightforward as acidic buffer solution, because for acidic buffer solution, to find pH, you can directly use the formula pH equals to pKa plus logarithm times the concentration of conjugate base over concentration of weak acid. Okay, but in this case, we have to follow these two steps to find the pH of a basic buffer solution. Now, before we're gonna start to solve this, it's better for us to draw the situation out. I like to draw the situation out so that I can better imagine what is going on and I know what sort of things that I need to work with. So the first thing that is provided to you is the if you look here, you have 200 centimeter cubic and 0.10 molar of the weak base. Okay, so we have that. So the first thing that is given to you, we have the base. So let's say that is the base that is given. So this is the NH3. We have 200 mil or centimeter cubic with the molarity of 0.10 molar. So this is what the question gives about your weak acid. Remember, this is your weak acid right here. Okay, so that is the weak acid, and it is mixed with 200 centimeter cubic of 0.20 molar of this salts. So that is the salts. That is your salt. The salt right now, it's in the form of liquid because you have a volume and concentration. If the salt is given in form of mass, the salts will be in solid form. Now, so we have the salt solution here. So that is NH4Cl aqueous, 200 centimeter cubic with 0.20 molar. So we're going to be adding this weak base with the salts together to produce a buffer. So when you add these two things together, you will be making a buffer. So you have a buffer solution. You have the weak base, and you have the salts inside. This is the buffer that we have formed. So what is the volume of the buffer now? So the volume of the buffer will be 200 plus 200. So your buffer will have 400 centimeter cubic of volume. It's very important for you to know what is the exact volume of the buffer, because we need to find the molarity of your weak base and also molarity of your conjugate acid or the salts over here inside your buffer in order for us to use the Henderson-Hasselbach equation. The concentration that we have over here, you cannot take this concentration. Okay, so it's a misconception when you get questions like this. This is the initial situation before they are being added together. So what happened usually for the misconception, students will take these concentrations of the weak base and also the salts, and they will plug that in directly into here, and that is incorrect, because the concentration that we are referring right here will be the concentration for the volume of the buffer. And for this situation, since you have your salts in the form of aqueous, so you have to remember to add up the volume together to get the total volume, and the total volume will be the volume of your buffer. And this is the volume that we're going to be using to find out the concentration of your weak base and the concentration of your salts or conjugate acid here. So before we're going to find the concentration of the weak base and also the conjugate acids for the buffer, we have to determine the number of mole for the weak base. So in the beginning, like what we have visualized over here, we have both of them in separate beakers. So we have to find out what is the number of mole of weak base and what is the number of mole of your NH4Cl. And remember, if you can find the number of mole of NH4Cl, we can find the number of mole of the NH4 plus. Okay, so to find out the number of mole of weak base in the beaker of the weak base, the question gives you the molarity of the weak base, which is 0.10 molar, and we have the volume, which is 200 centimeter cubic. And to find the number of moles, simply have the molarity multiplied by the volume. So we have 0.10 molar times with 200. We have to change that into decimeter cubic, and we are going to be you're going to have 0.02 mole. So by finding that, you have 1 mark here for determining the number of mole of weak base in the beaker of the weak base. And moving on to the other beaker that contains the salts of the weak base, to find the number of mole, we're just going to use the same formula, molarity times volume. Okay, so the molarity is 0.20 molar times with 200 over 1000 decimeter cubic. And the number of moles should be around 0.04 mole. Okay, in the case of NH4Cl, we do know that mole of NH4Cl is the same as mole of the conjugate acid, which is NH4 plus, because the salts here will be completely dissociated to form NH4 plus right here. Do you remember that? The salts, the NH4Cl aqueous salts will be completely dissociates in aqueous solution, because this is your salts, and you'll have NH4Cl aqueous completely dissociated to form NH4 plus aqueous with the chloride ion. This is the reason why if you can find the number of mole of your salts, you can find the number of mole of your conjugate acids. Okay, remember, this is the conjugate concentration of the conjugate acids as well. Okay, by figuring out the number of mole of NH4 plus, you get another 1 mark right there. Now we have found the number of mole for both species that will be forming the buffer solutions. So we're going to transfer that information into this situation. We have talked about this just now. When you have the weak base solution in a beaker, and you have another beaker with the salts, when you mix them together, the total volume will come into 400 centimeter cubic, like what we have talked about in the beginning over here. So this is the situation that we have drawn from what the question gives in the question. So when you mix 2 solutions together to form the buffer, we have a new volume, which is 400 centimeter cubic. So we have found out the number of mole of ammonia, the weak base, and the number of mole of NH+4, the conjugate acids inside your buffer. And now we're going to find what is the concentration of the weak base in the buffer and concentration of the conjugate acid in the buffer. We take the number of mole. So in this case here, we're going to take the number of mole, 0.02 mole NH3. So you're going to divide with the new total volume, which is 400 centimeter cubic. So that is about 400 over 1000. And the number of mole for that should be about 0.05 molar. Okay, and then for this 0.04, 0.04 mole NH4 plus over 400 over 1000, we should be having a value of 0.10 molar. These are the values or molarity for the buffer that we can put into the Henderson-Hasselbalch equation. By finding out the value, you get 1 mark right there, and you get another 1 mark right there. We will take both of the molarity values now, because these are the values for molarity for the buffer. Then we can plug that into the Henderson-Hasselbalch equation, POH. Okay, so NH4 plus concentration is the concentration of the conjugate acid, and then this is the concentration of the weak base, just like what you have written in the beginning. This is the Henderson-Hasselbalch equation. And we're just going to plug in all the values inside. So you get POH equals to, remember, P is negative log. And then the value of Kb is 1.8 times 10 to the power of negative 5. Okay, so the value of Kb is given in the question, which is 1.8 times 10 to the power of negative 5. So Kb value is there, given. Okay, so that is the Kb value. And plus log, okay, so the conjugate acid, the molarity is about 0.10 molar, and for the weak base we have 0.05 molar. You solve this and you get the value of POH equals to 5.0. You get 1 mark for using the Henderson-Hasselbalch equation, and you get another 1 mark for getting the value of POH. We have found the value of POH, but the question wants us to find pH. Remember, we have done this. So we have found the POH, and now we're going to use this formula to find your pH. The value of POH that we have figured out just now is 5.0. So we're just going to replace that. Okay, we found out that the pOH is 5.0. Therefore, the pH value is going to be about 9.0. You get 1 mark for using this formula, and you get another 1 mark for getting the right value of pH. Now we're going to look at another example in which we're going to have the same buffer solution like what we had over here in the first question, the same buffer solution, but this time we are going to be calculating the pH of the buffer after you have added a small amount of strong acid. So this is what the question wants. You need to find out what is the pH of the buffer solution, this buffer solution, and this time after you have added a small amount of strong acid. This is right here is your strong acid. So the situation now is you have your buffer, okay, and this buffer, remember, is prepared by adding 200 centimeter cubic of your wick base with 200 centimeter cubic of your salt solution. And the total volume is 400 centimeter cubic. This time you're going to add a small amount of hydrochloric acid. So we're going to add a small amount of hydrochloric acid. And what happened to the total volume then? Right now, we'll have a buffer solution that has been added with HCl, and now the total volume would be 401.0 centimeter cubic. So this is a very important piece of information because we're going to use this later on when we want to plug in the value into the Henderson-Hasselbach equation. This is the situation that we are having now, and we want to find out what is the pH after we have added a small amount of strong acids into your buffer in here. So first step is, before you're going to add the hydrochloric acid, we have to figure out what is the number of mole of NH4 plus, like what we have done in the first question just now. This is how you're going to do it. You're going to find out the mole of NH4 plus from the concentration of the salt solution. Okay, you're going to use the formula of molarity times volume. Then you get the number of mole of the salts, and do remember the number of mole of salts will be the same as the number of mole of your conjugates, acids, NH4 plus. Why? Because of this. This is what we have talked about just now. The salt solution will be completely dissociated, and therefore, if you have 1 mole of your salts here, you will get 1 mole of your conjugate acid, because salt is completely dissociated in aqueous solution. And then you also need to find the number of mole of the weak base being used in the buffer solution. Same like what we have done in the first question just now. The question gives you the concentration. So this is the concentration of the weak base and the volume of the weak base. By using the formula molarity times volume, remember, don't forget to change the volume into liter or decimeter cubic, and therefore you will get the number of mole of your weak base. By doing that, they will give you 1 mark for each. Okay, you get 1 mark for here and 1 mark right there. After we have figured out the number of moles of your conjugate acids and then your weak base, now we need to look at how much HCl is being added. Now the question gives the concentration of HCl 1.0 molar and the volume of HCl 1.0 centimeter cubic. And from these two information given, we should be able to find out the number of mole or the concentration of H plus being used. Okay, do you remember? Okay, you do remember that mole of HCl is equals to mole of H plus. Why? Because of this equation over here. The strong acid will be completely dissociated. Therefore, 1 mole of your strong acid will be producing 1 mole of H plus. So if you can find the number of mole of HCl, we can find the number of mole of H plus. So we're going to be using the same formula, molarity times volume. So we have 1.0 molar, that's times with 1.0 over 1000 decimeter cubic, and the number of mole will be 1 times 1.0 times 10 to the power of -3 mole of H plus. This is a very important piece of information because we're going to put this into your IACF table later on to find out the final mole of your conjugate acids and your weak base. So by doing this, you will get 1 mark. So we're going to take this number of mole of H plus and also the number of mole of NH4 plus, number of mole of NH3, and we will be plugging in that into the IACF table. But before we're going to do that, we need to remember what is the reaction involved now. So we do know that in your basic buffer solution, which consists of NH3 aqueous and the salts over here, there are 2 components that will be playing a very important role in maintaining the pH of your basic buffer. We have number 1, NH3 aqueous, and number 2, NH4 plus aqueous. So which one of these 2 components will be reacting with the additional H plus? Do remember that when HCl aqueous is added, we are adding H plus into the system over here. So we're going to be having this. It will be added inside your basic buffer solution. So the question now, between NH3 and NH4 plus aqueous, which one of these 2 components of the buffer will be removing H plus? Because the buffer wants to remove the H plus, because the buffer wants to maintain its pH. So to maintain its pH, it must remove the additional H plus from the strong acid. Which one of these will be doing that? This is the base. This is the conjugate acid. This is the acid. Remember, that is your conjugate acid, and this is the base. This is from the acid. So acid and acid, do you think they will be reacting together? No. For that reason, NH3 aqueous will be the one reacting with your H+. So the reaction now will be NH3 aqueous plus H plus aqueous. So this is the equation that we're going to take, NH3 aqueous plus H plus, and we're going to put that in your IACF table like this. Okay, so this is the reason why we have NH3 aqueous plus H plus aqueous to produce NH4 plus aqueous on top, because the additional H plus, okay, remember, this is the additional H plus comes from the HCl, and NH3 aqueous from the buffer will want to remove that. Okay, now let's fill in the blank in here. So initial mole of NH3 aqueous, we have that 0.02. If you go back to your calculation, okay, so you have 0.02 for NH3, 0.04 for NH4 plus. So you're gonna put that into your IACF. Here you'll get 0.04. We do not have this initially. Okay, we don't have that one yet. We don't have addition of NH3. The question doesn't say that you add more base into it. And we don't have addition of this. The question doesn't say that you add this into the buffer solution, but we do have addition of H plus. The addition of H plus is about 1.0 times 10 to the power of negative 3, as what you have calculated in here. Okay, so that's why I said this piece of information is very important. And then what about the change? The addition H plus will be removed by the NH3. So it will be consumed. So this one will be using this one will be used up. So minus 1.0 times 10 to the power of negative 3. The reason why you have minus, again, because this one is on the reactant side. So the change will be minus. And here will also gonna be minus. But on the other side, you have plus 1.0 times 10 negative 3. Because you're gonna be producing more of this through the reaction of NH3 with H plus. So you're gonna add together. So you get this much of NH4 plus being produced. So at final, what you have is 0.019. This one will be left 0. This one will be 0.041 mole. So you get 1 mark for this, 1 mark for that, and also 1 mark for the balance equation, the reaction, the correct reaction on top. Now we're going to take the final mole value and we're going to find the final molarity. Okay? To find the final molarity, we have the final mole. Okay, so we have the mole final for NH4 plus, we have it 0.049, okay, 0.041, sorry, 0.041 mole, and mole final for NH3 is 0.019 mole. So what is the final volume then? What is the volume final? And what is the volume final? Remember, in the beginning, we have worked out this final volume, which is 401 centimeter cubic. So that is the final volume. Okay, we have 401.0 centimeter cubic, 4.01.0 centimeter cubic. Therefore, concentration NH4 plus final is 0.041 mole over 401.0 over 1000. And we get about 0.102 molar for this one. Concentration final NH3 0.019 mole divide by the final volume 401.0 over 1000, and we get 0.047 molar. Okay. So by finding that out, we get 1 mark. We've got 1 mark over here. Okay. So we're going to take the final molarity now. You're going to plug into your Henderson-Hasselbalch. So now the POH is negative log 1.8 times 10 to the power of negative 5 plus log. So on top here is 0.102, 0.047. Okay, so these two values are the concentration that we have figured out here. Okay, so you take these two values, you put into your Henderson-Hasselbalch, concentration of conjugate acid, concentration of your weak base, and you get the POH value equals to 5.08. By doing that, you get 1 mark here, 1 mark there. So to find pH, pH plus POH equals 14. So pH is 14 minus POH. Your POH is 5.08. Therefore, pH 14 minus 5.08, the pH value is 8.9. So you get another 1 mark here and 1 mark right there. Finally, we're going to look at the last example, but this time we're going to be adding a small amount of strong base. Okay, so this is the strong base. NaOH is your strong base, and we are still using the same buffer as what we have used for the first question and the second question, and the buffer volume would be 400 centimeter cubic, and we're going to add 1 centimeter cubic of strong base. So now the final volume would be 401.0 centimeter cubic. Remember, this volume will be very important at the end of your IACF table later. So, like what we have done for the first two questions, we're going to find the number of mole for NH4 plus before adding the sodium hydroxide. This is the method that we have used just now. We use molarity times volume, and we get 0.04 mole of NH4 plus aqueous. Remember, mole of your salts will be the mole of your conjugates. Acids, NH4 plus. Why? Because salts is completely dissociated. And also we have to find out the number of mole of NH3. Okay, so this one is NH. We're going to find for NH3. So question gives the concentration of NH3, and you have the volume. Again, we're going to use molarity times volume, and we get the number of mole of your weak base. These two number of moles, again, before we're going to add NaOH. So by doing that, you'll get 1 mark and another 1 mark. How much NaOH is added right now? The question wants you to find the pH value when you add a small amount of NaOH. So we have to think about how much sodium hydroxide is being added. So we're going to work in terms of mole. Question gives the concentration 1.0 molar, and we have the volume 1.0 centimeter cubic. And do remember the number of mole of NaOH will be the same as the number of mole of OH minus. Why? Because your strong base, sodium hydroxide, will be completely dissociated. That is the reason why the facts here and the facts right there. To find molarity, to find mole, we have to take molarity times volume. The molarity given is 1.0 molar times with 1.0 over 1000 decimeter cubic, and the number of mole would be 1.0 times 10 to the power of negative 3 mole of OH minus. So with that, you get another 1 mark. Again, do remember, this one is going to be a very important piece of information later. So we're going to take this value of mole of OH minus, we're going to put into your IACF table. Okay, next we're going to be thinking about if we are adding NaOH, for sure we are going to be adding OH minus into your buffer solution. So this is the basic buffer solution that we have been using since question number 1. And of course, when you have NaOH, this NaOH will be completely dissociated to form OH minus, and this OH minus will be added into your buffer solution. Do remember, inside your buffer system, we have two components, the base and the conjugate acids. Between these two, one of them will be removing the additional OH- being added into your buffer system. If for the acid, the conjugate acid will not going to be reacting with the acid. This time, the conjugate acid will be reacting with your OH-, because just now in the example of acid, if we go back to the example of acid here, we have H+. So between these two components of your buffer, NH3, which is the base, will be reacting with the H+. Okay? And this time, since you are adding a small amount of strong base, NaOH, you have OH-. So you're going to be reacting with NH4+. So the equation now that we need to consider is NH4+, aqueous plus OH-, aqueous. You're going to use that in your IACF table, and this is what you get. Okay? By writing the correct equation or the buffer action on top, you'll get 1 mark. Okay, remember, this one is from the NaOH. So we're going to fill in the IACF table. Initial mole for NH4+ is 0.04. OH-, initially we haven't got this one yet. NH3, the initial mole is 0.02. And water is liquid, so we're just going to be ignoring that. We don't have addition of NH4+, and we don't have addition of NH3. Therefore, we don't have that for addition. But we do have addition of OH-, which is 1.0 times 10 to the power of 3 mole. And this OH- will be reacting with your conjugate acid. Therefore, it will be consumed. So this species here will be consuming your OH-. Thus, you have negative 1.0 times 10 negative 3 for the change. Over here as well, because they are going to be reacting together and to produce this much of NH3. So if you see here, the change value will be following the value of addition of OH-. On the reactant side, it will be negative change. On the product side, it will be positive change. So final mole, you get 0.039. This one will be 0.00. And on this side, you get 0.021. So these are the final mole that will be important now for you to find the final molarity. Okay? By doing this correctly, you get 1 mark for initial, 1 mark for addition, 1 mark for change, 1 mark for your final mole. Okay, so next step is to find the final molarity of your NH4+ and NH3. Mole final, we have figured that out for both through your IACF table over here. Okay, and then volume final, we have figured that out in the beginning of the question right there. So this is the final volume when you add these two things together. And how do you find the final molarity? So you're just going to use that formula and you get your final molarity 0.097. Same goes to this. So you're just going to be taking the number of mole and divide with the final volume. You get 0.052 molar. So you get 1 mark for this, 1 mark for that. You take the final molarity now. Finally, you can put that into your Henderson-Hasselbalch equation. So the concentration of your conjugate acid here is 0.097. Okay, for that one. For this one's NH3, the concentration of your weak base is down here, 0.052. From where did you get that? From here and from there. So the pOH value would be 5.02. And by doing that, you get 1 mark for this, 1 mark for that. Finally, to find pH, we need to consider pH plus pOH equals to 14. So pH equals to 14 minus pOH, and the value of pOH is 5.02. So 14 minus 5.02. So the pH value is 8.98. Get 1 mark and 1 mark right there. So that's how you're going to find the pH value of the buffer solution after you have added a small amount of strong base.